Welcome back. Today I'm going to do an example of a data acquisition system, and we're going to start with the transducer. We're going to work our way through the analog circuits, the analog filter, and the software method in order for us to measure temperature. That's my goal here. Okay. If this sounds familiar, this is indeed Lab 9, but I am following the design example in the book in section 10. 6, so if you're doing Lab 9, you might want to look at the Excel sheets that I'm going to show you today, as well as look in that section in the book. All right. Lab 9 is fairly open-ended. I hope you like the way we've changed the structure, a la the discussions we had about the class early in the semester. We've morphed the schedule to unoverlap the lab, so next week you do Lab 9, the following week you do Lab 10, and then we do Lab 11, so we'll have about 1 week per lab. Okay. The other thing about Lab 9 is it's fairly open-ended. I want you to learn, and the exact specifications of what it is you built, I don't care really. I am going to start with these specifications, but feel free, of course, to change the range, to change the resolution, to change the accuracy. I don't really care. I do want you to learn about some things. Okay? I want you to learn about the transducer. And you go, hey, John, why are there wires sticking out of your shirt? That's my transducer. I'm calibrating it to 36 degrees. It's under my armpit. Okay, so I can't wave my arms until I'm done with calibrating. Okay? That's a transducer. I want you to learn about a bridge. Okay? The bridge is what's called a secondary conversion element. The thermistor is a primary sensor. In other words, it converts temperature to resistance, and we'll see that curve in a moment. But the bridge converts resistance to a voltage difference. So the signal here is encoded as the difference between V2 and V3. And so a bridge is a classic way to have resistance type transducers generate voltages that the system can then convert. This is a differential signal which requires a large input impedance and a large common mode rejection ratio, and that is exactly both the necessary and sufficient conditions to use an instrumentation amp. We saw last time that we used a low-pass filter for two reasons. One is to improve signal-to-noise ratio. For instance, if I'm only interested in 0 to 10 hertz, 60 hertz, 22 kilohertz, 16 megahertz, those are all noises, and so we would like to remove them. And the other reason we used the low-pass filter was anti-aliasing. I mentioned a term before, and I'd like to bring it up again, and that is called the power supply rejection ratio. And essentially what this is a measure of the amount of noise on your power line. Okay, so if the power line has 10 millivolts peak-to-peak noise on it, the question becomes, how much of that noise shows up right here? How much of that noise shows up in my signal? That ratio is called the power supply rejection ratio. And if I don't use the shunt diode, it's going to be 1-to-1. Okay? If I don't use that shunt diode, if I just take my power line and I plug it into the top of that bridge, all of the noise from the power will show up in my signal. But the purpose of this reference, because this voltage right here is 2.33, independent of the 3 volts, this 2.5 volt signal here will be very low noise, and therefore my signal will be very noisy. Okay. Like I said, I don't care really what your resolution is, but you should know what it means, and we'll show you ways to measure it here in Lab 9. All right, so what's the difference between a requirement and a constraint? Nothing really. One says what you must do and the other says what you must not do. Basically, you got to get it done in a week. So we expect you to use the parts we've already given you. But if you want to use other parts, I don't care. You should have used 1% metal film, low noise resistors, but you're going to use the crappy carbon stuff you get check out. Yeah, you should have used COG capacitors, but you're going to use the crappy X7 F stuff that you get from checkout. All right. All right, this is the essence of Lab 9. We're going to measure temperature. And so the data flow graph is one of the first things we build, and it shows you how I'm going to put all the pieces together. The transducer converts temperature to resistance, the bridge resistance to voltage, the amplifier voltage to 0.33. And then we're going to use the timer to trigger the A to D converter. Okay, so we're going to use a timer-triggered A to D converter such that we have absolutely no jitter, no sampling jitter at all, because what we're going to do is we're going to generate an edge on the timer. Okay, this is going to be internally in hardware. We'll generate an edge at the sampling rate. Okay, so this is at FS. And that is going to trigger the A to D converter. So in 319K, you wrote to a register to do a processor start. Okay, right? You used a processor-initiated start, but here in 445L, we're going to use timer-triggered start, and therefore we're going to get an ISR, an interrupt service request, from the A to D converter. The A to D converter itself will interrupt when the sample is done. And the sample that gets generated, that gets converted, will be one which occurred exactly at this time, independent of when the software ran. Okay, so there'll be virtually no sampling jitter. So if you look at the clock, the 16.00 megahertz clock, which is then with the PLL going to get me an 80.000 megahertz bus clock. That is going to be the precision, so to speak, of the sampling process. Okay, so any jitter I have in the clock will show up in my sampling jitter, but that jitter is pretty small because I had a crystal. What's the rule about interrupt service routines? Short and bounded. What do you know about liquid crystal displays? Fat and ugly in terms of software time to do stuff. So that means that the main program is going to do liquid crystal display, and the interrupt service routine is going to collect the data. If you want to run a digital filter in there, that's fine, but you generally want to be short and bounded, and we're going to use a FIFO linking data structure to pass the data from the background to the foreground. All right. Question?
So you're using a timer in order to trigger the ADC. So say there are values that we write to the register which says that the maximum sampling rate is 125 kilosamples.
Gotcha. Okay, what Mahesh is alluding to is when you do Lab 9, there's going to be a bunch of clocks. And let me sort of demystify the clocks for you. 80 megahertz is your bus clock. That tells you how fast it's fetching opcodes. Okay, and it executes about an instruction every 1 or 2 bus cycles. Okay? Then we have an ADC clock. Okay? This is how fast the ADC runs. Okay? And so, for instance, we're going to connect it up internally to when you turn its clock on. We're going to connect it up to something that's around 16 megahertz so that it can create a maximum sampling rate of 1 million samples per second. Okay? Or we could make it a little bit slower, so this maximum sampling rate is 500 kilohertz per second, or 125 kilohertz per second. Basically, the slower I run this clock, the more accurate it is. Okay? And the data that I get will be more reliable. What's the other way to make it more accurate, by the way? Remember? We could slow down the ADC clock. So you will see a register where you get to choose 1,500,000 or 125K maximum FS. And the slower you can run, the more accurate. But there was another thing we saw in earlier labs. 16. He said, what's the difference between the ADC clock and the max sampling rate? And that is, it's a successive approximation register, and I got a lecture for that later. Basically, it takes one bus cycle to do a bit. You got 12 bits, it's going to take, not bus cycles, it's one ADC clock cycle to get a bit from my A to D converter. So I got to make 12 guesses in my successive approximation register. That takes 12 ADC clock cycles. So if I want to sample 1 million samples per second, I'm going to have to clock the ADC at 16 million hertz. Okay. Did I answer your question? Yes. Yeah. The point that Mahesh is getting at is I haven't got to the interesting one. Okay, that's the maximum FS. The actual FS is determined in 319K was the rate in which we started in software. In 445L, it's going to be the rate of this timer 0A, which is going to be 100 hertz. Right? We saw that last time. If I sample at 100 hertz, that's well over the Nyquist rate for my temperature. And so there will be a timer clock at 100 hertz. And this rising edge in the timer clock is going to trigger an A to D start. That's the sampling rate, that 100 hertz. Okay? And these three clocks get people confused. Because when you set the frequency in the A to D converter to either 1,500,000, maybe there's a 250 in there too, or 125K, that doesn't set the sampling rate. That sets the speed of the clock and therefore the maximum sampling rate. But one more thing before I get back to teaching, and that is, how else can I improve signal to noise? The hardware averaging. Okay. The hardware averaging register, which can average up to 64 samples, okay, is a wonderful thing to do in this lab because it can sample at 125,000 samples per second, and you only need 100 samples per second. So this is a good example of turning on that hardware averaging register and collecting in hardware 64 samples averaged together. Get one interrupt when it's done. This is a great chance to do that.
Is it always necessary to have a FIFO to store data, or can I have a global variable? Okay,
so a very interesting question, and that will be on the final, so let me answer it for you. All right. ISR is passing data to the main program. Okay? What I need to know is, I need to know what the maximum rate, or better, the minimum time between the production of data. Okay? And over here, I need to know the minimum rate or the maximum time between the consumption of data. Okay? I'm passing data from the background to the foreground. This is an input device. Okay? And now the question comes, now I could look at averages. Okay? On average, the rate in which I produce has to be less than the average rate, the rate, not the time, that I consume, or it will crash. Now, when I hook them up, the average will be equal, okay? But if I don't lose any data, the averages will be exactly equal. But I'm thinking about I'm defining the ability to produce and the ability to consume. These abilities, I have to be able to consume it faster than I produce it on average. But I can allow the maximum rate to temporarily exceed the consumption rate. How? What magical data structure allows the data to come in temporarily very quickly? The FIFO, okay? That's the basic idea. And the answer to Mahish's question is, do I need a FIFO or do I need a mailbox, which is the fancy word for a global variable and a flag, okay, is the following comparison. Okay? If I look at the minimum time here, okay, which in our case is exactly 10 milliseconds, right? I'm sampling at 100 hertz. So both the minimum, the average, and the maximum production rate is exactly 100 samples per second, or 10 millisecond time. If this time is greater than the maximum time to consume, then I can use a mailbox. If I used a FIFO, it would only go up to one element, okay, 0 or 1. So that's actually a way to prove this is true. Is stick a FIFO in there, profile the FIFO, you'll see it only has 0 and 1 elements. Okay? Does that answer your question? Now, if the averages are bad, then it crashes and you can't get an answer. What I'm going to do is calibrate my thermistor. I'm going to get this curve. Okay? I'm going to get this curve. So what I'm doing is I'm going to do a 2-point calibration. Okay? I'm a mammal, so my body's pretty much isothermal. It's about 36 degrees centigrade in my axilla. Okay? So I'm going to use that as a temperature point. Okay? Can you see that? So we got to remember 64 point. All right. This is a Excel spreadsheet that's on the website. Download it. The way these work is where it says blue. We're going to be able to type into. Okay, so I just did a calibration point. And interesting is I'm not too far off from when I calibrated it with my good thermometer. But it's the same thermistor I calibrated before. Oh boy, I forgot. Anybody remember? 64 point. Anybody remember what the number was? But that was my first calibration point. The second is I need to go over to the thermostat over there, okay, and see the temperature in the room, okay. Okay, can you see this number right there? Okay, this time I'm going to remember it. 129.2. Okay, 129.2. It's a little bit warmer than my office. So what do you think the temperature in the room is? 24. Okay, so it's just, we went over to the temperature in the room. We saw it's 24. I got 2 points. Now it turns out that the shape of this thermistor is a weird exponential. Or logarithm, depending upon whether you're going from resistance to temperature or from temperature to resistance. You can see in this equation here that the actual curve is related to Kelvin and not centigrade. So you see the 273.15. But what will happen is 2 points and 2 coefficients can get me the relationship whether I'm going from resistance to temperature or temperature to resistance. I can get those 2 coefficients. Okay? If I were to zoom down and look at the plot, okay, I just got the relationship down here. It's over here. Okay. Between the temperature of the world and the resistance of this transducer, okay? And it's highly nonlinear. Okay? It's highly nonlinear. But the nonlinear is not bad. We got a computer. We can linearize it. Now, if you go to checkout and you get you can see that this is defined as 100K. If you look at this as approximately 25 degrees is approximately 100K. You might have a 50K or a 30K thermistor. That's fine. If it's a 1K, then it's weird. And if it goes down, if it goes the other direction, it's even weirder. So I expect it to go down with temperature, and I expect it to be in the 30, 40, 30, 50, 100, in this case, 200K range. All right. All right, the next thing I'm going to do is something bad happens to a thermistor if you dump power into it. It is a resistor. Okay, so it will convert electrical energy to thermal energy. And normally we don't care. If the resistor in your circuit gets a little hot, I don't care. But in this device I do, because that's my transducer. And so if it turns out if you put a whole milliwatt into your thermistor, it'll increase by 2.5. Well, it'll increase by, okay, the milliwatts, do the units. If I put 2.5 watts in, I will get it to increase by 1 degree centigrade. Okay? And that's really bad, because 1 degree centigrade heating in the transducer is a 1 degree centigrade error. Okay? So what I want to do is to reduce this power by a factor of 10, a factor of 100, so that I don't self-heat it. So we'll see a column where it calculates how much power it's putting into the thermistor. You remember there was a bridge, okay? And so now I'm going to design this bridge. I get to design the reference that I'm going to use to power it. And here again, I'm using 2.5, not 3.3. And then the first choice I'm going to do is this R1 and this R2, which will be the same. I want to choose those resistors so it doesn't self-heat. So I'm going to go down to my column here and look at if I choose a 470 ohm resistor right here, that will specify how much power is in the thermistor in this column, and therefore the corresponding temperature increase in the transducer. You can see at 470 ohms, I'm increasing the temperature only by a millidegree, well below my measurement. So you'll see that if you try to put 10K in there, it'll get too hot and your thing won't work. All right? So the first choice is to choose a resistor here. Something wonderful happened, by the way. Something wonderful happened. It's not a very complicated circuit, but what can you tell me about the relationship between V1 and RT? Is it linear? No, but what is it? Okay, just by the way, to do that, what is that? 2.5 volts times R1, RT, over, oh, that's 470K, by the way. Sorry, yeah, 470. Okay, 470K plus RT. Very nonlinear. And you go, oh, John, that's bad. I got a nonlinear transducer. Now I got a nonlinear circuit. You know, but as you know, 3 lefts is a right. Okay? If I turn left 3 times, I'm facing right. And so this nonlinearity is actually wonderful. And look at how much more linear the actual response is compared to the transducer, right? The transducer was very nonlinear, but the actual response, because of that nonlinear circuit, is actually not too bad. Not linear enough to be linear, but not too bad. Okay. All right, so I choose 470. Now the next thing I'm going to choose is R3 to set the maximum temperature. And this, like I said, I don't care what maximum temperature you got. But in this case here, let's say I want to go up to 40 degrees right here. See that? 40 degrees is going to be centigrade is my largest temperature. And that, for this particular thermistor, is going to be 51K. So I'm going to choose a resistor less than 51K and put it in R3. So the R3 resistor is my, the R3 resistor right here, specifies the maximum temperature. Okay, so I got one more variable here, and that's the gain of my amplifier, which will set the minimum temperature. Okay? And so you can see here that, okay, let's see what happened. Okay. Well, this illustrates a wonderful problem that a lot of people have doing Lab 9. Right here, it's telling me in order to hit my minimum temperature, which was specified right here of 10 degrees, okay? In order to hit that minimum temperature, I'm going to need an amplifier gain of 4.35. But as we saw, the instrumentation amp that you got in class last week or on Monday only has a minimum gain of 5. And so it wants a resistor value of negative 300 ohms. Don't go to checkout and ask for it. Okay? So what I'm going to do, to fix this problem, I can do one of two things. I can increase the size of that R1, or I can just, Texas sharpshooter here. Let's just pretend I was trying to do 15. Right? And it won't work in an ice bucket, but, whatever. Say, works now. Okay, now it wants a gain of 5.8. And it wants a resistor right here of 249 point whatever. And so I'm going to type in here the actual resistor value that I've chosen. I want to make the gain smaller than needed, so I want a resistor bigger than needed, so I like put 330 ohms in there. Yeah, 330 ohms. And so my actual gain is going to be 5.61. And then if I go down, I see that there are no discontinuities here. Okay, there are no discontinuities. All right. So I have the temperature on this axis here going from 15 degrees, that's fixed point 15 degrees, up to 40 degrees, and there's my A to C value going from 0 to about 4,000. It makes this wonderful, nice table that shows you the different values for 50 different temperatures, the relationship between the A to C value and the corresponding temperature for this thermistor. Better than this table is, where'd it go? Come on, it's down here somewhere. Right there. It's even better than that. It gives me 2 pieces of data structure that I can copy into my program. Okay? So I can take this guy here, right? Copy that, which is a table of 53 data points, 51 in the middle and an extra point on the inside and the outside, and then the corresponding temperature data here. And so now I can use a table lookup with interpolation. So if I were to measure 2,000, right? So if my A to D converter said 2,000, okay, what I'm going to do is I'm going to look at the corresponding. Let me go up and do it on the table. It'd be easier. Okay. Right. So if my A to D converter says 2,000, that means it's somewhere between 24.00 and 24.5, and then I'm going to use linear interpolation to get the exact value in between. Okay? With me on that? All right, so let's build it. Okay, let's build it. Let's go over to my thing. Okay. So we had 2.5 volts, 470K, 470K. There's my thermistor. Now, if your thermistor is, has a waterproof coating, you can dunk it in ice, but most of them don't, so don't stick it in ice. Okay, I got to get the sign right. Again, this voltage here, this V1, will always be bigger than V2, and so I'm going to connect it up that way. I'm going to power it with 3.3 volts, put a bypass capacitor on here, and then I'm going to use that 330 ohm resistor here in the RG spot. I'm going to ground pin 5, and also ground the power pin. And right there, I'm going to have a signal that I want to measure. So this signal here corresponds to this VS column here. The cool part about this is I can use this table to test my circuit. Okay? I can use the table to test my circuit because all I have to do is go to checkout, find myself a 200K resistor, stick it in my circuit, and then I should see about 0.74 volts there. I should see about 2.8 volts at that part of my circuit. I should do my A to D conversion and get about 3479, and then my software should give me something about 1700. If I were to put in a 200K resistor in place of the thermistor. So I can use this table to test my circuit. I got one more thing I want to do, and that is design the low-pass filter. All right, last time I did a 25 hertz filter. Do you want me to do that again, or want me to do a different one? I'll do it again, do it right this time. How's that? Okay. Another design template for you. It's called LPF. All right. So again, this is the circuit from the book that we did last time. I'm going to fill in the cutoff frequency that I want, 25 hertz. Okay. And then it's going to give me some values that I can't get from checkout. So what I'll do is I'll say, well, what if I could get a 0.22 and 3 0.22s, and I'll make one of them be a 0.44. Okay, so one of them is a 0.44. I mean, two of them together in series, parallel, are 0.44, and one of them is the 0.22. Okay? But if to do so, I'm going to need a resistor of 20.49, and so I don't have that one. I'll 20K. Change the colored ones. There we go. So in this particular filter, I ended up with a 25.57 hertz filter. Okay, so now I'll go build it. Okay. 20K, 20K. .22. This goes into the plus side. The minus side goes around like that. This guy's grounded. This guy here. And I got 2 0.22s microfarads. And that goes my ADC. Okay, so I just built lab. Well, you'll have to. We'll do it for yourself, but just like that. Questions? All right. Let's go back to this one here. All right. So in summary, what did I do? I used the bridge to get me a voltage. I used the instrumentation amplifier to do the differential gain. You're going to have a gain somewhere between 5 to 10. That's my expectation. We saw what happened if I get stuck and I wanted a gain of 3, right? I could either increase these resistors here, or I increase the minimum temperature. Or I choose a different chip, but that's way too hard for us. Okay. The amplifier was to do range matching. That was the essence of the Excel sheet, was to range match the temperature into the resistance, into the A to D converter range. We want it to be fast enough, so we need the amplifier to pass the signals of interest. And then we talked about this loading business. This happened here. If you think about a bridge, let me just do this one fairly easily. 470K, 51K, and there's V2. Okay. This is a fairly simple circuit, and if you were to model this circuit as an output voltage and an output impedance, right, you could create a Thevenin equivalent of this circuit. Unfortunately, it's going to have an output impedance of 51K. Or less, actually, or more. It's not going to be very good, but luckily for us, we have an input impedance of the instrumentation amp, which is huge compared to 51K. So this was an essential reason to use the instrumentation amp. And so when I ask on the exam, okay, if I ask this question on the exam, what if I took a bridge and I connected it to the other differential amplifier? Remember that one? Okay. R4. And the gain here is R5 over R4. Okay, that's the regular differential amplifier. If I built this circuit, it wouldn't work. If I built this circuit, it wouldn't work. Why? I just violated the rule. Okay? Right? So again, if I wanted a gain of about 5, I would put 10K and 50K here. 10K and 51K here. Okay? But the input impedance of this, okay, is 61K. That's not 4,096 times bigger than that. Okay? So this doesn't work because of impedance loading. Okay, so again, the rule is we want the input impedance of the next stage to be 2 to the n times bigger than the output impedance of the current stage. Okay, that's a rule. All right. The amplifiers have a wonderful thing. They can also be frontline for spurious inputs. Somebody plugs 120 volts AC into that connector because they're bent on doing something stupid. It'll burn out this instrumentation amp, but probably will not burn out your processor. Okay, so these chips have a bit of a fuse to them. Okay. Somebody asked, should I put all my chips in sockets? I hate sockets. Okay, I got a rule. I'm calling it right now. You come to my office, lab 11 doesn't work. It's a connector. I'm sure it's a connector. Yeah, that's the reason why all the stuff doesn't work. And this is also important for life, and that is if I look at resolution, which is the smallest change in my ability to detect temperature, it's going to be determined by the electrical noise related to, converted to the equivalent voltage or temperature or whatever. That electrical noise will determine the resolution of your system. All right, that's what I just did. So there are the rules, what I just did. And there's my rules. You remember, it does satisfy the necessary condition, which was to have a differential input, and two of the three sufficient conditions. We needed a large input impedance, and it turns out common mode in our system. The bridge has got a wonderful thing. All electromagnetic field pickups are going to come into the bridge and create common mode, which is why we use it. So we want to reject common mode. And I did that one. Again, when you're doing this, the math's not too hard. This is correct. All right, sidebar for the right answer and the practical answer here. The real answer is to use C0G capacitors in every place but the bypass capacitor on the amplifier. So if you go back, I erased it. But we're going to use in the filter, we should use C0Gs, but practically for Lab 9, you're just going to get what you get, and it won't work very well. Okay. Same thing with resistors. We want low tolerance, high accuracy resistors, but again, I don't care. You gotta. To some extent, it's very nice to have noise on your lab, by the way, because then you can measure it. You can see it. Yeah, if you had a very low noise system, it's actually very complicated. It turns out when I do this, I have this awesome machine. You can't have it because it's expensive. Okay? But what I have is a bucket of gallium. Now, if you ever go to the store and try to buy gallium, it's not cheap. Okay? And this gallium is in a container. Okay, let's actually show you what it looks like. It actually is a container and is in a container. Sorry, it's both. Okay? So what I do is I put my device in here. This is my device I'm testing. This guy is in another container. Okay? And then I put that container in a, oh yeah, and it cost me this cost me $2,000, by the way. And this one cost me $1,000. And I put this in a precision water bath. All right, I'm getting there. The fun part's coming. And what I do, this is under very large pressure. You know what happens to an object if you put it under pressure? A lot of pressure. A lot of pressure. Yeah, the melting point and the freezing point come together, okay? Such that if you're, and it's called a triple point, an object that exists in all three phases at the same time, solid, liquid, and gas. Okay? And it turns out if you take gallium and you make it, this has to be close to 27 degrees. Okay? If that's close to 27 degrees centigrade, this goes to 27.7776 degrees. I actually got a four decimal digit precision reference, if you really wanted to know what the temperature was. Now, the rest of us, you know, mortals, who don't want to spend $3,000 just to calibrate their Lab 9, just say it, don't spend the money, is if you take water and crushed ice, and then you insulate it. This will probably go down to 0, you know, plus or minus 1/10 of a degree. It's close. And you put your object in here. No. But again, don't do this because your thermistors have bare wires on them, and put bare wires into water, it shorts out. Okay. But if you have crushed ice and water mixed together, it gets close to 0. All right, here's Lab 9. The thermistor converts temperature to resistance. The circuit converts resistance to voltage, and the ADD converter samples the data. The software translates that to temperature, and it's plotted temperature versus time on the graph and displayed numerically here. If we increase the temperature of the probe by grabbing onto it, we can see that the temperature rises both in the graph as well as in the number. So in summary, we're going to use software to use a table lookup. The spreadsheet will actually give you that table. And then what we're going to do, and then we'll use fixed point to go on the display. Read the lab manual. I show you how to do the graphics. And then we're going to do one more calibration. Is after you've built it, what I'm going to do is I'm going to take the temperature probe from checkout, and I'm going to produce a 1-point difference, a 1-point offset, such that when you go to checkout, it'll look right. Okay? So rather than do a 40-point calibration, we're going to do an initial rough calibration with our armpits, and then we're going to do a 1-point calibration using the temperature probe from checkout, and you'll add a temperature such that your measure device exactly matches the temperature probe that you've gotten. So when you go to checkout, it'll look perfect. But we won't tell the TAs who cheated.